For this video, we'll be finding the midpoint Riemann sum, and we're using the same function, f of x equals x squared plus 1. We're going to start at x equals -1 to x equals 2, and we're going to use a delta x of 0.5, 1/2. So we'll divide these into 6 equal subintervals. So the difference between the left hand, right hand, and midpoint Riemann sums are all where you find the height. For the left hand, you go to the left hand side for each subinterval to find the height. For the right hand, you go to the right hand side. And predictably, for the midpoint sum, you look right in the middle. So we will be looking at -0.75, -0.25, 0.25, 0.75, 1.25, and 1.75 to find those heights. So I will go right in the middle up to the function either side and down to draw it. So right in the middle. And there is some symmetry on this one as well because we're using a parabola. Okay. So up to here. And this one. Okay, so for the midpoint Riemann sum, we're finding the areas of these 6 rectangles and then adding them together. And just like with the other sums, if the bases are the same, you can actually factor out that base. So each one of these will have a a base of 1/2. So I'll pull the 1/2 out, and then I would have 6 different heights. And I find each of those heights by evaluating this function at the midpoint of each interval. So when I evaluate this function at -0.75, I get a height of 1.5625. When I evaluate it at -0.25, I get 1.0625. When I evaluate it at 0.25, I get the same function value. The next one is 0.75, so 1.5625. And then I'll actually value it at 1.25, so 2.5625. And then finally at 1.75, so I get 4.0625. And when I add up all of these, divide by 2, I have the midpoint Riemann sum. Okay, so Riemann sums in general, and I'll do trapezoidal in the next video because a trapezoidal isn't really a Riemann sum. You're not adding up rectangles, you're actually adding up trapezoids. But for all Riemann sums, this is what you're doing. You are finding the sum, this is our sigma notation, from the first to the last rectangle. So if you have 6 rectangles, you're adding up from 1 to 6. If you have 5 rectangles, from 1 to 5. C sub I is the place where you're actually finding the height. So on the left-hand side, C sub I would be the x value on the left-hand side of each subinterval. Midpoint will be in the middle, right hand on the right-hand side. And it's f of C sub I because you're taking that value, that x value, and plugging into your function to get the height. So this whole thing represents the height of each rectangle. This is the x value where you find the height, where a height is found. And then delta x sub I, this represents the base of each. And we have it for, it's not always the same base, they have the sub I on here because you don't have to have equal subintervals. If you do, it's really nice because you can factor this out, you can pull it out, but you don't have to have equal subintervals. You could have one rectangle with a base of 2 and one rectangle with a base of 1/4. It depends on what they give you. So if you look at this, you have base times height, and you're adding up the different bases and heights up to the number of rectangles you have. So this equals that rectangle estimate of the area. Now it is related to this. This sigma for sum, and here's your sum symbol in integration from 1 to n. Okay, those are your different rectangles. We would be adding up from, say, x equals a to x equals b. F of c sub I, that's our function height. We're adding up different function heights. And the delta x is your dx. So there is a definite relationship. And when you actually apply the limit to this, because we know we get a better estimate, the more rectangles we have, a better estimate for area, you would do the limit as as n approaches infinity. So you're getting an infinite number of rectangles of this sum, and it is actually equal to this definite integral. Your delta x, when you have an infinite number of rectangles over some interval from a to b, gets very, very, very small. Okay, and that's when it's starting to look like our dx. It's a very tiny thing. So one thing you can think about is if you are under this curve here, you're adding up very, 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 very small rectangles. You're adding up a bunch of different function heights from a to b. And as long as it's an infinite number, you're actually going to get the area underneath that curve.